the second session, the title Software, on the idea that it's not just about almost metaphysical ideas about how to do science and what science is really about and how we should all be collaborating. It also translates into how do we actually get about doing our stuff? What are the practices, and very importantly, what are the tools that allows us to do particular forms of practices? And for the first speaker in this session, we have Joachim Vandekerckhove. Sorry, it's kind of not half Flemish, half US pronunciation of it, who is based at University of Irvine in California, where he runs the Cognition and Individual Differences Lab, also known as the SIG Lab. And before that, as you might be able to guess from the name, he has been at many institutions of great renown, among them the University of Leuven in Belgium. So took all of his degrees there before going to the US. And if you go and take a look at his website, you will come across not just an enormous amount of interesting papers, but also a large repository of software and tools as to how to get about doing these things and how to get about sharing not just the finalized publications, but also the scripts and the tools available in order to get about thinking about it. So Joachim, we couldn't really think of a better person than you to open this session. Take us away.
Well, thank you for that comprehensive introduction. For the record, the various institutions of great renown refer to where all these other people are. Right? So the not that the University of California does not have its own bit of renown. So thank you also for the invitation to this workshop and to the organizers. This morning's session was excellent to begin with. So today I decided to give a slightly different talk. It's not mostly about software. It's actually still more about the open science and the sort of reform in science that's going on, and I might touch on the ideas that were talked about earlier today also a little bit. So one thing I'd like to talk about is something that we've been doing in my lab for, recently, and something that I think is newish and somewhat interesting, is the idea of randomly sampled experiments and the goal of what we refer to as robust testing. And so this is a large collaborative project, so these people are all involved. Beth Berrybold is my graduate student who actually runs point on this study. But you'll see that quite a bit of work goes into it. But it does all go back to this idea of reproducibility, and the next couple of slides are going to be a rehash of things Christine already said this morning, but I made these slides on the plane on the way here, and I didn't feel like taking them out because they're here now. So the reproducibility, I'm sure if you're in this room, you've heard this word at some point, and is what is commonly or is now often said to be in crisis. So Monia Baker, this paper in 2016, is the Nature paper that had that survey where people are being asked if the reproducibility is in a major crisis or maybe in a little bit of crisis. And people tend to endorse that, at least one of those things. But it's not like a niche thing, right? Even in 2015, National Academy of Sciences wrote a pretty big review on the topic of scientific reproducibility. National Institutes of Health think of it as an important review criterion in the U.S. Congress, the U.S. Congress, in its infinite wisdom, has weighed in, and industry has weighed in. So this quote is not due to Rosenblatt; it's due to Eric Topol, who's sort of a big pharmaceutical CEO. And he's worried that lack of reproducibility is a threat to the biomedical enterprise, as you know, it clearly and obviously and trivially is. So reproducibility is important. But I grew quickly tired of the long and unending sequence of one demonstration after another that things don't replicate or things don't reproduce, especially in the scientific literature. I'm just going to stipulate to that now. So yes, that's a thing. Empirical findings poorly replicate in a number of different fields, and I'll just go even a step further and say much of the public literature is suspect. Like we can't necessarily trust many of the empirical claims made in the literature. And I'm not completely alone in this, right? So in the same survey by Monia Baker, people not only said that they were worried about reproducibility, but also that scientists should do more to boost the reproducibility of their own findings, and that this idea came, or the reproducibility boosting measures came in a few categories. The really obvious one that everybody will mention is do better statistics. The slightly cleverer one, I think, has more to do with design than with inference. It's a better design of experiments so that you get both internal and external validation. And something people call robust experimental designs, which sounds really cool, but I couldn't for the life of me find an actual definition of this in any relevant publication. But I'll get back to that. Because I thought this was this is an interesting word, robustness. Robustness, I'll get back to where I think that word appears in an interesting or informative way. But it came, I thought the idea of robustness, the concept of robustness, became important immediately after the first reproducibility project paper was published, the big science paper in 2015 by the Open Science Collaboration. So they had this litany of results, all these things don't replicate, and then there were a bunch of sort of popular media responses to that failure to replicate. And one theme that showed up quite a bit was the idea of hidden moderators, right? And I think of this as the well-but argument. So people say, yes, it's true that things don't replicate in this particular paper, but there are differences between your study and the original study. So one that was apparently unironically used by someone was that the replication study was done in Amsterdam, but the original was done in Nijmegen, and also that the original was done in the late 90s, but the replication was, this number is wrong, it was in the mid-2010s, as explanations for why reasonable people should not have expected things to replicate. But that doesn't seem like a reasonable claim, right? If your empirical claims are only true in Nijmegen in the 90s, then what are we to make of this, right? And this is, like I said, as far as I can tell, this claim was made unironically, but it's indicative of a bunch of claims people make all the time, where they say, well, you made this irrelevant change, so obviously it shouldn't have replicated. We found this on a fifth Wednesday in the summer, and you didn't. And this isn't new, right? So the idea that hidden moderators occur and that they are the little demon that make results not replicate is as old as science. So Berna earlier today talked about Boyle a little bit. And Boyle has this, so I didn't find this, Richard Morey attended me to this, that Boyle has this little passage in a bit of research about how to purify antimony. And he says, well, that in his furnace it's very successfully made, but then sometimes we fail to make it and other people fail to make it in their furnaces, and there's blah, blah, blah. And he writes here that, well, some of these artists are researchers, right? Some of these researchers believe fondly that there is a certain respect to times and constellations that is requisite to the producing of this. So he said that depending on which star sign you're under, maybe that makes it more likely that you'll get pure antimony versus the contaminated or the unpure version that they were sometimes creating. Turned out much later that the source material can be pure or impure, and that actually made the difference. So there was a genuine hidden moderator, but the search for hidden moderators, like why does this thing happen sometimes and not other times, is an obvious and reasonable thing to do, and is very old. And yet, in much of the explanations that we hear, at least on the psychology side of poor replicability, many of these claims that hidden moderators must exist to explain this difference don't really hold up to scrutiny. And I'll give you an example. Before I do, I, like everyone else, need to set down some terminology, and as is very obvious, my terminology will be idiosyncratic and different from everyone else's. So it's good practice. But I feel I need to do this because some of these words are, obviously they're used differently by different people, and some of them are overloaded in a way that is unproductive. So I will say, and I will use the word replicability as ensuring that other people can repeat the study procedures used. Right? That's one. The second one is reproducibility, which is the act of ensuring that other people can repeat the analyses that were performed once the data are given. And then I want to introduce a new word, which is a concept people use all the time, but it gets conflated. Robustness, which is how do we ensure that other people obtain the same findings or come to the same conclusions given all these other things, right? Because just because you are able to execute an experiment the same way as someone else did it doesn't mean you're going to come to the same conclusions, because there's natural variability and other things that are going to be different between replication attempts. And then finally, and I'm not going to talk about this too much, is generalizability, which is a bigger brother to robustness. Right? Generalizability is, do I find the same thing in a wildly different context, such as not in a lab? So how can we ensure that results translate from the small, limited context that we have to the bigger context that we care about? So these things, I think, are sort of a ladder of strength that a finding can have. Right? And some of these are relatively easy to obtain. So replicability, in the limited way that I've defined it here specifically, is not very hard to obtain. You just have to make sure that your materials are available to everyone, and that you properly describe how you did the experiment and all that, so that someone else can repeat the study. Similarly, with reproducibility, it gets a little bit trickier, but you can publish your code, and you can make your code reproducible by letting us know what the assumptions of the code are and what versions of what software you're using, and so on. But then robustness, this is the one that gets tricky. Like, how do you ensure that if somebody else does the same experiment, how do you optimize the probability that they're going to find the same thing, come to the same conclusion? And it seems to me that that's what robust design is meant to be. Right? So I'll talk about that mostly today. And then generalizability is even harder, probably requires some extra level of abstraction. This is no longer, so robustness and generalizability are no longer just features of the data that you obtain, but are features of how the design of your study relates to the real world and is representative and all that. I won't talk too much about generalizability. Does that all make sense, everyone? Am I allowed to make these different? Okay. All right. So the word robustness makes sense to me because of how it's used in other fields of science and engineering. So for example, robust statistics is the branch of statistics that focuses on making sure that you get the same results even if your assumptions are violated. Right? So the idea is that a robust statistic has good performance if the data can be drawn from a wide range of possible probability distributions, especially non-normal ones, and still show good performance. A kind of similar definition exists in the programming world. So there's the idea of robust programming, which basically means that you should program in such a way that if the user does something completely crazy, the computer doesn't catch on fire. Right? Which sounds like a joke, but isn't. If you work with Windows, you often see that blue screen of death. That is the computer acting as it is supposed to, because otherwise it might overheat or do something wrong. So robust programming is a style of program that focuses on handling the unexpected and then still behaving properly. And robust engineering is perhaps the most relevant to what we do or our scientific practice. It's building a state such that the technology, product, or process is minimally sensitive or insensitive to any factors that might cause variability. Right? So if external variability is to be expected, how do you build a bridge that will still stand even if the conditions change in a way that you hadn't fully anticipated? And that seems to be a really good analogy for what we want to do. If I build an experiment and I come to some conclusion, I want to build my experiment in such a way that if you do it in your lab and something is different in your lab, you're still going to find the same thing. Right? That's my working definition of robustness. Is very close to this here. And that seems like a good goal. Optimizing for finding the same thing while still sort of making reasonable claims and reasonably drawing conclusions from data. Obviously, as Berna gave the example, you can make super robust methods by just making your claim independent of the data, right? But that's not what. So robustness is not the only thing you should aim for. But you might as well take it into account. So in that list of requirements that we had, from replicability to reproducibility to robustness, what is robust design? So I'm thinking of this in terms of, what does it achieve? What does robust design achieve? So a really low bar for robustness, I think, would be if you do the exact same thing again, but exactly the same thing. Like in my own lab, I get the same participants back and I make them do the exact same thing. Right? If I don't find the exact same thing then, or I don't find something really similar, then something's really wrong with the way I'm doing the experiment. So that's a low bar. There's a sort of a medium bar where I might want to say, well, I want my results to extend to a replication or a repetition of this study, but that's allowed to differ in some ways that I think are theoretically inert. Right? If there are some theoretically irrelevant differences, for example, the fact that your lab is in a different city, or that the temperature in your lab is slightly different from the temperature in my lab, or so on, anything that's irrelevant is allowed to differ, and I still want the same results or the same findings to come out of the experiment. That seems like a good kind of criterion. That's something that we want, if for no other reason that if this does not occur, the replication police is on your case, right? So the way I think about this is in very sort of statistical quantitative terms, namely that there exists some population of experiments that is interchangeable for my purposes. So when I'm testing a claim, I could do this experiment or I could do this slightly different experiment, and reasonable people who are all competent researchers, they might come up with a slightly different experiment. So all these possible small variations of the same study or the same experiment asking the same question, they form a population. And I want to make a claim about that entire population, not just the one experiment I might have chosen. And obviously generalizing to a population is hard. It's not completely trivial, but it is a thing that we do all the time. And usually we do it through random or possibly non-random sampling. So sampling is a thing that usually licenses extrapolation to from a sample to a population. So that's what we're going to do. And this practice is something that we've dubbed randomized design. And the way it works is this. So typically when we do an experiment, we have some manipulation and we have some operationalization of the thing we measure, and we have some way of manipulating the thing that we're interested in. And when we do that, we want the effect or the observation to extend to things we might have done differently testing the same claim. But now you have to wonder, well, what are the things I might have done differently? That's not immediately obvious. But it turns out people have thought about this. So there are these groups of people here who talk about, well, what is the scope of a claim? Like, how far does a single empirical claim go? And there's the oldest one is from Cronbach, who is the Cronbach from Cronbach's alpha, but it's also the Cronbach from generalizability theory or G theory. And he talks about a universe of generalization. So whenever you make a claim, there's implicitly a universe associated with this. Simons et al., they call this constraints of generality. So they have this idea that when you make a claim, you want this to generalize, and what they say when you write a paper, you should make it explicit what you want to generalize. And similarly, Kennan and Rubinstein, they have a more statistical sort of bent. They talk about the boundary of meaning. So I make a claim, and this claim is sometimes verbal and a little vague. So what are the possible data patterns or quantitative shapes that reality could take that are consistent with this meaning? What all of these kind of have in common is that they invoke this sort of spatial metaphor. Right? There's a space that is highly dimensional in which experiments live, and you can arrange the experiments in this space according to a set of different dimensions. And the claim is then, well, inside this highly dimensional space, in some region of that space, an effect might be true, and in some other region it might be false. So again, what we want to do is generalize across this population of experiments, or across this sort of space, this multidimensional space, and to do that we can sample from it. And in practice, what you do is you start with your basic experiment. We've done this a handful of times now. This is the first one we did. Started with a subliminal queuing effect that we found published in the journal Cognition. And the basic experiment is on the phenomenon of subliminal queuing. So the subliminal queuing, if you're not a perception psychologist, just means that you give a participant some cue on the screen, some bit of information, and they have to act one way or another depending on what the prompt is. But then the way the prompt is presented in such a way that it's not consciously visible. But then it turns out people change their behavior anyway, even when the prompt isn't consciously available. So this sequence of frames is shown very rapidly, where there's some masking, and then there's the prompt, which is a V or a B, I believe. And then there's another mask, and then there's a task. And the task is to hit the bullseye to click in the middle of a bullseye. And depending on what the prompt is, you have to do this as fast as you can or as accurately as you can. Right? So the cue tells you to favor speed or accuracy in this task. And the cue is either masked or it is not. And when it is masked, we call it subliminal. And even so, in this original paper, the participants managed to change the speed accuracy trade-off, so they acted faster or more accurately depending on the cue, even when the cue was presented subliminally. So that's the basic experiment that you start with. And then what we do, and we do this in a kind of a crowdsourced way, is we try and identify all the features of that experiment that a reasonable and competent person might have done differently. So there are some really obvious ones, like there should not be anything special about the letter V and B, right? If it doesn't work with a W and a P, then something's wrong, right? So that's something that is clearly arbitrary. The color of the stimuli, so you saw that bullseye was red in the center, but if that's yellow, you should get the same effect. The brightness of the stimuli should, as long as it's visible, should probably not make too much of a difference, although maybe it will. Another one that I'm kind of big on is that the identity of the participant shouldn't matter, right? If I get a new participant in, I should probably find the same thing, and so on. So we managed to do this quite easily for, in this case, I want to say 15 or between 15 and 20 dimensions of the experiment that we thought were completely arbitrary and that you could vary quite easily. So we identified many of those features, and most of them we genuinely think are theoretically inert, like the characters used. And some of them we're actually not sure if they're theoretically inert, and we're just going to explore and see what happens, such as some features of the timing of the presentation. Some of those should be inert, and some we don't actually know. But especially the theoretically inert features, they are the ones that are not specified by a verbal claim. So if you verbalize a theory, or somebody who verbalizes the effect of subliminal queuing, they probably wouldn't have said, and it has to be a V versus a B. They would probably have just left that to your imagination. So these theoretically inert features, they get lost in the translation of a verbal claim or they're not specified in the verbal claim. You have to make them up when you come up with an experimental design. So all these dimensions are independent variables, and they span a space that we call the method space in the same way as Berna used that phrase earlier. So it's a set of possible experiments. And the theoretical statements that we're interested in are now functions over this method space, where we say, well, an effect occurs in some regions but not others, or it might be bigger in some regions than others, and so on. And an experiment obviously is a point or maybe a small area in that space. And so what we did, and this turned out to be really simple to do, is so Beth, the student, she coded up the experiment just in PsychoPy, just a typical way of coding up an experiment. And at the very top of that experiment were 5 or 10 lines of code that randomly generate all these features of the experiment that we don't care about from some given set of distributions. And then after each block of the experiment, we had it resample itself. So each block of the experiment is sort of a unique little micro experiment. I feel there's a slide missing here where that information should have been. So each block of the experiment is its own little micro experiment, and so every participant gets a unique sequence of, I want to say 14 or 16 of these micro experiments. And at each little micro experiment, we call them micro experiments because each of them only has 32 trials, right? And in each of those, we think of them as interchangeable, and then we're going to jointly analyze these in a essentially, we call it a meta-analysis, not strictly speaking a meta-analysis because we have all the data available, so it's just a big joint analysis. But between these experiments, we then want to see whether the effect occurs in the aggregate, does it occur in certain regions of the method space versus others, and what is the variability among these experiments in general. And what we find is something reasonably straightforward on the in the aggregate. So there's this little graph here, where if we look at the unmasked stimuli, we see that if the Q instruction is to be fast, you see people get less accurate. So this is accuracy here. If the Q instruction is fast, people get less accurate. If it's accuracy, they get really accurate. And especially importantly, you see this occur also when the stimulus is masked. So this looks like the effect is sort of reproduced, right? But it doesn't stop there. Because now we can break this down back to the sort of micro experiment level. Now, for example, what we can do is we can look only at the positive control trials, so only the unmasked trials where the Q is clearly visible to the participant. And now I can plot this distribution of effect sizes in each of the micro experiments. So what you see here, and I've color-coded these by whether the individual micro experiment gives evidence for or against the presence of an effect. Right? So you see here these little blue bars, they're actually little micro experiments that are more consistent with the null than with the alternative, and these orange ones here are more consistent with the presence of an effect. And this looks entirely reasonable, right? So for the huge majority of the micro experiments, we do find that there is we do find an effect. Obviously, that's not terribly surprising because this is just a participant doing what they're told, right? So they visibly see a Q, and the Q is to be fast or accurate, and there's some effect size measure that captures this, and it does. So it turns out participants are more accurate after an accuracy prompt. But that's not surprising. But if we focus only on the mass trials, the effect looks a little more fickle, right? So now the majority of these micro experiments support no effect, right, over a yes effect, and there's even like this tiny little group that seems to support an effect in the opposite direction. And still here, we also see this lots of level 2 variability. So we see a large amount of variance between these micro experiments, such that there is this subgroup of the micro experiments that shows the subliminal effect, right? So here is, apparently there's some population of little experiments that we could have done. So again, a reasonable colleague could have picked any one of these to do their replication, and if this is any indication, they would have replicated It doesn't look very robust, though, right? Because with a much greater probability, we would have selected a microexperiment or one of these experiments that that supports the null. But again, there might be some effect under limited conditions. But of course, we made all these experiments, right? So like I said, every participant did 14 of these blocks, and we had several hundred participants. So in total, we had something like 5,000 individual micro-experiments. So we have a lot to work with. We can now go and drill into the data a little deeper. So a thing you can do if you have all these, these little micro-experiments and all the settings that were used to generate them is you can now go and explore this method space through a technique that we call planned metaregression. But it's just a big joint model where we try and predict, given some of the independent variables that we have, and we have many, where do we or do we not find the effect? And one thing that you're meant to look at if you do subliminal queuing studies is whether you need to measure whether the conditions that you think are masked and subliminal are actually masked and subliminal. So what we did after each of these micro experiments of 32 trials, we did another 32 trials just asking the participant to identify the stimulus, like did you see a V or a B? So we call that the Q identifiability conditions. So we did that under the unique conditions of each micro experiment. And now we can introduce that as a covariate. For example, it's one of the independent, it's strictly speaking not an independent variable, but it's one of the things you can use as a predictor. And it turns out that you get this beautiful sort of sigmoid function where in the subliminal range where the detection accuracy is less than 60%, say, you sort of reliably get a null effect. Right? So this is the subliminal range, and this is the observed subliminal range of all the possible microexperiments. Right? So this is not, this is regardless of what the design was meant to do. Right? So if the settings of the experiment were such that you believe that this should be subliminal, but actually you're in this region, it's not a subliminal manipulation. So what we find is in the subliminal region, the effect sizes are really close to 0, whereas as soon as you leave the subliminal region and the more you do, the stronger you get this effect size, which kind of makes a lot of sense to me. But I find this the less interesting analysis. The more interesting is the one that makes no sense to apparently most other people. So I'm somewhat idiosyncratically, I find this more interesting. So I'm going to introduce a covariate into this meta-analysis that totally should not matter, like say the color of the target. And now I get, very predictably, I get this absolutely flat function. Right? So I get two flat functions, one for the subliminal presentation, one for the supraliminal presentation. But this, I think, is interesting, because now I'm showing, well, between all these possible replications of the same experiment, I get the same results throughout. Right? So in the supraliminal condition, it looks like I get about this effect size. In the subliminal condition, it looks like I get about this effect size, regardless of what choices I might have made. Right? And that seems to me the interesting claim here, is that this is a claim to robustness. Right? So here, you have to do the extra little effort here of splitting them out by something that matters. But even if I hadn't done this, you can collapse between these groups and you just get a flat line somewhere else, right? So the robustness claim is independent of whether there's there's a true effect going on somewhere else. So conditional on actually being observed subliminal in this particular set of experiments, that's the effect, the claim that subliminal effect seems robustly absent, which is the interesting kind of claim that I was interested in making. So more generally, so we call this a meta study, for lack of creativity, I guess. So the goal of this is to make statements at what we think of as a slightly higher level of abstraction. So rather than saying we have this finding in this really limited set of circumstances that happen to be true in our lab, we actually make the claim, well, this this effect holds in a broader set of circumstances, even beyond the ones that we actually tested. All right. And this jives, I think, really well with all this talk of generalizability and generalizability theory that people have talked about for a while. Except this is sort of well defined and quantitative. Like there exists this universe of intended generalizability, and I can tell you exactly what it is. And if you do that, you get to do something like defensive design, in the sense that you're now able to design an experiment that, with more confidence than usual, you could port to someone else and say, here, now you do this thing again. Make sure they have all the materials and the codes, and so they don't make mistakes. But with somewhat greater confidence, I think you can say that they'll find something much closer to what you found, right? Because you've now eliminated all these, or you've not all of them, but the goal is to eliminate as much as you can the innocuous differences that might exist between labs that may or may not have a result. And this turns out to be sort of feasible, relatively cheap. So you saw the results, and you saw the tiny little error bars and everything. That's because we had 300 participants, which is 6 times more than we usually have. But if I do this analysis again with just 50 participants, I get the exact same pattern, just with slightly wider error bars. Right? So we learned afterwards that the amount of data we collected was a bit of overkill. And the actual programming, the actual difference in programming up the experiment was trivial. And the analyses that we did on them are not particularly complicated. They're sort of relatively run-of-the-mill hierarchical linear models. Yeah. So putting that back into what I feel like the context of this workshop is. So I think robustness is an interesting thing to establish for a particular reason, namely, I think most real effects are probably robust. So if this is a simplification of the method space where there's some independent variable that we don't particularly care about on the horizontal axis and the effect size on the vertical axis, I think most effect sizes probably hang out at roughly the same height. And I feel somewhat confident in this because we see this happen relatively often. Right? So for example, all these many labs projects, they tend to go one way or the other, right? Not exclusively, but in the majority. There's not much evidence that like empirical effects sort of come on capriciously and then disappear again. And secondly, I think robustness is sort of practically, or again under my definition, is practically interesting because it seems to be sort of a prerequisite for actual predictive power, right? And that's probably what underpins practical applicability. So if you can't make robust claims about, say, the effectiveness of a medical intervention, you probably shouldn't be doing it. But I have the impression that many people in the social sciences, and especially the people who write op-eds about hidden moderators, seem to believe this is the case, where over the method space, the effect is usually absent unless you nail the design and you get it absolutely right. But outside of this, a belief seems to be that effects are very fickle. Right? And that's the so this is what you kind of have to believe if you do an experiment in your lab, or if your grad student does an experiment in the lab and they come back with a null result, and then you tell them to change something absolutely tiny and try it again. Right? If that sounds like a reasonable thing to you, then this would appear to be what you believe, right? That the effect lies on some peak or on some ridge in this method space. And if you believe this, then conducting really finely tuned experiments and doing so in an artful way with flair is really important. But I don't think it is, genuinely. And regardless of what I think, and regardless of whether this is true or the previous thing is true, if this is the world you live in, you can't I misused my own word. You can't possibly come to robust conclusions. because there is no way to systematically differentiate between fickle effects that only occur under really limited circumstances and statistical flukes. So they're going to be systematically hard to distinguish. So if this is what you think, if this is what you think the world looks like, and again, this is just a personal suspicion, right? But if that's what you think, then your own effects, for example, not reproducing in your own lab is not going to be surprising to you. And it's not going to be like a huge red flag that you're doing something wrong. And whether you believe this or this should impact how you do research. Right? So these have different balances of exploration versus exploitation. Whereas here, if you find an effect, you should probably call it quits, because the odds that you'll find it again are lower. Right? Whereas here, if you find an effect, you should try and replicate it, because you'll probably find it again. Right. So, so again, I think this is a more productive, I think this is both more likely to be true and more productive way of thinking about effects. More generally, something we don't think about a lot in the social sciences, as far as I can tell, is that there exist methods that are optimized for various things other than finding an effect. Namely, sensitivity is the one that's for finding an effect. But you can build research methods and styles of experimental design and even statistical inference that are optimized for robustness or generalizability that are different. Right? And I feel that these could be used more because they're not used now. And one technique that's kind of counterintuitive is the one that I was talking about just now. So you add variability to your design to improve robustness. So it's the opposite of what you're taught to do, right? You're taught to have everything tightly controlled in the lab and walking this really narrow path in the method space so that you can nail down an effect. Whereas the thing you should be doing is letting things vary and be more like a field experiment in your own lab, so that you can, in order to make your claims more robust, to improve the likelihood that you'll find the same thing again. And these are things that, so this generalizability theory that comes out of the psychometrical literature on random effects, where the same idea is present. Otherwise, these are not difficult things to implement. So these are things you can do in your own labs without having to buy new equipment or whatever. So that's all I wanted to talk about, and I wanted to make sure that I emphasize again this is big collaborative work with a bunch of other people. I got references here.